Section 2 of the thermodynamics chapter is really about the big view. So we're going to call it the specifics because it's all to do with specific heat capacity, specific latent heat, and is very much looking at the numbers and how the numbers signify different things as we warm things up or as we cool them down. So we've got mirror graphs of the same material, gradients are the same for each section, length is the same, that kind of idea. So what we use about this, but because we've just been looking at the particles, although this work all was discovered before we knew about particles for sure, we're going to go with the explanation so you can see how everything links together. Okay, so that by the end of this section you can start to link together all the explanations with a visualization of a model in your head. So, what are the specifics? Well, there's two types because we have two different things going on. We have sections on graphs where the temperature is changing, and then there's sections where there's no change. And knowing how to describe what's going on is pretty crucial for the exam. It's about using that language that will just get you those extra marks. Okay, so I've got a graph here. Just transfer it so we can have a bit more detail of that. And just to give you an idea, stepping aside from the topic, why have I not got units here? This is a sketch graph, so these are arbitrary units. It doesn't matter what it is. I could have degrees centigrade, I could have degrees Fahrenheit, I could have Kelvin. It doesn't really matter up the side. And along the bottom we've got the amount of energy going into it. Now of course if you have a heater, then the energy equals PT, so for a constant power this could be a time axis instead. Okay, so how much you've got it warming up. So, two flat sections. Notice that one's much bigger than that one. Okay, needs a lot more energy. Generally, again, this is for a generic material, but generally that is bigger than that one. We tend to find that the bottom stage is pretty steep, but again the gradients of all these three depends completely on the behaviour of the material, and some things are very odd, some things are very different. It's mainly down to the particle motion itself and the bonds again. So let's have a look at those. So I've got some descriptions which we'll try and tie on with the graph a little bit as well. And it's really just thinking about what's going on. So in the first stage what we've got is, as you can probably guess, we have certain key points. That is a fixed temperature, that is a fixed temperature, and you've got three stages happening between them, so these have to equate to solid, liquid, and over here we've got our gas. So how they behave, how material behaves, when we talk about specific heat capacity, we really need to start saying, well, where? Is it in the solid phase, the liquid phase, the gaseous phase, and beyond? So we could have, again, plasma and so on. Now this is indicative, this graph is indicative of a pure material. If you have things with different, for example, mixture, different materials within it, then these would not be pronounced. They wouldn't stick out like that really obviously. They blend much more blurredly, shall we say, blurred through the phase changes. Okay, so these are our three phases, to use technology, three states of matter, three phases of matter, just to kind of the idea that it's a continuum, which is why we use phase, and then there's these things going on in between. So, to start with in the description, solid is heated, it's transferred to the molecules, so again use that word molecules. Particles is good, but molecules is better. It's making them vibrate more, which means the temperature changes. So within our wobbly model that you saw in the video, what we've got going on is, I'm going to shorthand this after a while, the kinetic energy increases. Okay. But of course you've got bonds between them, but the key things is on average, again it's they're all varying all the time, but basically the bond energy, the potential energy, the stored energy is constant. Okay. When we get to the melting point, the molecules, as we have more and more energy, don't just keep going up in temperature, they stop increasing in temperature. So the temperature is that average kinetic energy of each particle, or of the particles. So they're not going any faster, so there's no change in that. So in other words, the kinetic energy is constant, but what is happening is the potential energy is changing. Okay. Now, it may seem a little odd, but what you've got going on is, because you're moving them further apart, the forces of attraction get less, therefore they're easier for the particles to move around, easier for them to transfer energy around to each other and so on. So potential energy is actually decreasing. Okay, now again, keep in mind that first box in the chapter, that's decreasing, the stage before that's increasing, and they're both constant. That change in increase there is a different size to the decreasing one. This stage, there is more energy in the whole substance than there is at this stage. Okay, so even at the phase change, there's more energy here than there is stored up at this solid state. Then we get to the next stage and it's increasing again, and so increasing in temperature. So again, what we've actually got is kinetic energy is going up, and because they are moving past each other, they're not really they're not bonded in the same way, so the potential energy is constant, and so on and so forth. Oops. So it just keeps changing phase. Here at the boiling point, again, not vibrating anymore. Temperature is constant, but the energy of the bonds at this stage, holding the whole thing together, it allows them to jump out. Basically, this needs a lot more to really separate those particles from each other, so it tends to have a larger area. Potential energy can drop to almost zero, depending on the conditions. So if you have it compressed, it's going to behave differently to if you just have atmospheric pressure. It just means how close together the particles are, and the closer they are together, the more attraction there is. Okay, so almost zero is what I've said there. It's very, very small, and I should say equals zero in an ideal gas, which of course ideal does not exist. So real gas is almost zero. In the calculations and stuff, it's basically taken to be zero. And then again, what we've got going on is they're getting faster and faster and faster as they move along. So if we go back, in the old days it was just down to this calculation, the idea, but what the reason is for it, the why, is definitely about the actual motion of the particles and the bonds between them. So if we take the graph and we wanted to find out how easy it was to change the kinetic energy of a particle, then what we need to do is just simply find the gradient. Okay, and that gradient, that change in temperature over energy change within the substance, well, that gives us some sort of value, which will be a constant. Okay, but that constant depends on two things. It depends on the material itself, the ability, the capacity to absorb that energy, and it also depends on how much you have, because if you've got twice as many particles, then you're going to need twice the energy. So we end up with the mass in there and some constant, which in this case is the specific heat capacity. Oops. Okay. So that's what we mean by specific heat capacity, how much energy it takes to warm up. So as you can see down here, this has a much bigger value in its solid state than the liquid state. It's much steeper gradient, and again we've got a large state here, but they can vary from material to material. Maybe the liquid is the one that goes up rapidly. Some materials heat up very rapidly. Water is actually quite a low rate, so it's a bit more like this. Gas heats up quite easily. Ice is pretty easy to heat up. Liquid water is quite hard to heat up, so it's a much longer time to use that energy to increase that temperature, and that's because it has what we define as a larger specific heat capacity. Okay, so that's the thinking behind the equation that you did at GCSE, and just to make sure that everyone's talking from the same rules, again, you may have used theta at GCSE, but what we've got here is we are going to look at an amount of heat transfer. Okay, so we've got delta Q. So if you go back to that universal laws of thermodynamics, we had delta Q equals delta U plus delta W. This is the heat going in that causes the mass to change of a certain capacity to change by a certain temperature. Okay, so increase there, increase there. If that's a decrease, then that heat is coming out. So again, it's an energy equation. The positive or negativeness just means the direction in which that energy is going in or out of the material. Okay, definition of specific heat capacity is that generally, if, and again a link back to here, if you're talking about a gas, you have to define other factors, so at what kind of temperature or what pressure that you're using it to. Okay, so this is this whole idea about that kinetic energy. Now I'm going to skip past this bit a second and we'll come back to another time. The flat pace, what we've got here is exactly the same. We have a rate at which we add energy on my graph, excuse me, and the only difference is we're not getting a change in temperature, but it does still depend on how many particles you've got. So if you have a constant solid, constant volume of solid, which changes to the same volume of liquid, which then changes the same volume of gas, you're going to have the same mass throughout. Mass will be constant. However, we're still going to need an amount of energy, and it will depend on this ability to break the bonds this time. So not the ability to store heat, but actually it's almost this idea of hiding the heat. So the heat didn't seem to do anything, and that's where the name latent came from, because it's Latin for hidden, so hidden heat. So the equation for latent heat, because you tend to go into phase change, definitely in A-level questions anyway, as well as heating up or cooling down. We've got the same kind of idea, but our Q in this case, or our Q going in, is a very fixed amount, and the crucial bit is these are not, although that's a change in there, it's a fixed amount. Okay, to make a certain mass melt, you're not going to have a certain changeable amount of heat, so that disappears. There is no delta, there's no change in temperature. So the crucial bit is, if you're asked to define this, it is without a change in temperature. Okay, and that's the bit that's needed to get the mark. Terms of times of units, that's where we get the difference between the two. So joules per kilogram per Kelvin, joules per kilogram. We haven't got the Kelvin because there's no temperature change. Okay, so this is this idea here, and again we need to be a little bit specific. So if we're talking about the specific latent heat, are we talking about the specific latent heat of fusion, which is melting, which sounds a bit mad because you're not fusing anything together. So that latent point is exactly the same size if we were cooling it. So although it could be called the latent point of melting, it isn't. It's fusing, because that's where when we're cooling down, there's something very definite going on as we rebuild those bonds. But that is your melt. Just be a little careful with language. This is your latent point of fusion, okay? But this is the actual points they're talking about, so it's that temperature, okay? So melting point, boiling point, often called that. Over here, again, most things tend to be in the liquids phase that we often find useful. So at the top end of the graph is the latent point of, evaporation. Okay, so again, they're different, so be very careful. If you're describing this or doing further calculations, are we talking about melting or are we talking about evaporating and boiling? Okay, so in the exam questions, it should be pretty obvious, something that just gets a little bit too hot. Now, how do we find it? Well, how to find the specific heat capacity is very tricky in the version that you did at GCSE. Basically, the result will be fairly terrible, and the main reason is because the temperature is affected not just by how much energy you go in, but also how much energy you're losing to the surroundings. So you have heat loss as well. So if you wanted to be really correct, I'm just going to put in brackets outside the block, we have plus H, and that is heat loss. Okay, and again, plus or minus depending if we're heating or cooling the substance. Okay, if we're trying to cool it down, specific heat loss makes it go down faster, which is great. If you're trying to heat it up, it makes it go up slower, the opposite effect. Okay, so plus or minus depends on that. But yeah, if we were to try and just stick the immersion heater in like you did at GCSE, and you take the temperature, well, we put our energy in, and that therefore goes into, that will be your work done by the electron, so that's your W. Okay, just like squeezing your piston. You will change the U, okay, of the internal energy of that, but you're also going to be really careful because you are going to also have energy escaping, okay, and just fit in, I'll call that H, so heat loss, okay, although it's actually Q, but let's not worry too much about that. So, work done, changes the energy of that. You can use the equation that we've just written down. However, in reality, because of that heat loss, it's not going to be right. So what you want to try and do is make the overall heat loss equal to 0. Okay, we could wrap it in insulation, so we have better insulating factors, so that means you have worse conduction and the heat loss is going to be slowed down. You can't stop it, but the rate of the heat loss is going to be smaller. Or more simply, there's a better method. Even if we were to surround that in a vacuum, suck convection and conduction, you'd still get the radiation. So the way to do it is actually make sure that if we are at a certain temperature above, okay, so this is room temperature here, I'm running out on this pen, excuse me a second. So if this is room temperature at this point, and this is basically a graph, what we do is if our temperature is above that line, above that temperature, and then we're going to get heat loss. Okay. If it's below, then the heat will be coming from the room and going in. Okay, so actually adding to the value, so it's heat gain. Now, if overall, during our experiment, those two are equal, if we add them up and they equal 0, then that will be H equals 0. So there'll be no heat loss overall. There's no error caused by heat coming in or out of the block. So how do we do that? Well, nice and simple in a way is that when we're heating, and we'll turn this into a graph now, we're heating over time, okay, and the temperature that we're looking at, well, what we'll do is we'll start at whatever temperature below room temperature, and we'll go up over time to above. Okay, so that is the same size, and what we'll find is basically the areas will be the same, so they'll kind of cancel each other out, that loss, and by using that gradient you should be able to get a really good value for specific heat capacity. Okay, so delta T over T, okay, if you multiply that by VI, then that's electrical energy going in, and so energy, time, and we then need the specific heat capacity after putting in the mass. So, great, nice, straightforward, but cunning, because what you're doing is you're thinking about the experimental design to think what's causing the problems. In this case, it's the heat loss. So how am I going to make it zero? You can't, but you can make it net zero by some of the time losing heat and some of the time gaining heat. Okay, so that's the key way of designing experiments, to try and reduce errors. Now, there's other ways. Okay, so if we go to our sheet here, we've just described basically an electrical method. Electrical energy in changes the internal energy. Bit of a description there. The continuous flow method is like your electric shower. So what this is, as hinted by the name, is you've got a continuous flow of liquid that you are, or gas, sorry, so any kind of fluid, and what you're doing is you're putting that through your heating section. Okay, so in your heater you're going to need a certain amount of energy. Okay, and it's that energy that goes into the equation. Well, great. We're looking for a temperature change, MC delta T. So by measuring a temperature change, we'll have T2, T1, if this is flowing from left to right. Okay, subtract them and you've got the temperature change. Nice and straightforward. Delta T. Okay, difference between the two. The problem is we haven't got a mass because it's flowing. So what we can do is we can use the idea of mass is density times volume. Okay, so if we know the density of the liquid, that's great, that will work, or the fluid rather. But we need volume, and we can't get that. But what we can do is how much there is in the heater, how much has passed through per second, which will give us mass per second. Now that might seem a bit odd, but everything has to be divided by T. So if we haven't got mass per second, what we're going to need is we need something else per second, or these multiplied by time. The obvious one to me is energy per second. And of course, if you think about that, that's the definition for power. So the power of your heater and the flow rate in kilograms per second and temperature change will give you that value there. Okay, so that's again fairly straightforward one, but it's just thinking slightly laterally. You haven't got a fixed mass, it's mass per second. If you had an electric shower, you can check it's working because you'll have the power of the shower, the electric power. You could fill up a bucket and see how much water flows through in a certain time, so you could get mass per second, and you can measure the temperature at which it comes out and the temperature at which it goes in. So, you know, it's a nice easy method for working things out. So this is called the continuous flow method and works really, really well. The harder one, you really need to look at the PowerPoint to get your head around this, but basically you have two substances and they need to go together, and usually, just to make it simple, at least one of them needs to be a liquid. Okay, so temperature 1, temperature 2, whichever one's the hotter one, it doesn't matter. You put them together, what do you end up with? Well, you end up with a beaker with something in it. There we go, genius. But temperature wise, you'll end up at a different temperature. Okay, temperature 3. And what you'll find using common sense is that if that's really hot and that's really cold, you'll end up with warm. If it's the other way around, that's cold, ice cube, in a warm drink, you'll end up halfway through, approximately, not definitely halfway. So basically, T1, let's say, is lower than T2, well, T3 will be in the middle there. If it was the other way around, it will still be in the middle there. Okay, so really straightforward logical idea, but when you're trying to do the math, it then starts looking a little bit complicated. Temperature change, well, that will be a temperature change from T1 to T3, whereas that will be a temperature change from T2 to T3, because they both end up at T3. So this gap here will be different size to this gap here, and that's where the maths can go wrong. Okay, so you just need to lay it out really, really logically. And again, think of how you do the layout. You have energy in going to energy out. Okay, how does that work for thermodynamics? That's going to be hot going to cold, or colder. Okay, so on your equation, you do the equation for the hot side, and then you do the equation for the colder side, and then you'll get the temperature changes in there. So you can lay it out nice and straightforwardly if you keep thinking of that method, and just be wary of that little trap there. Okay, so that is the third one, which is called method of mixtures. As I've said in the example here, I think it could just be putting water into a bath. Yeah, they don't both have to be. You don't have us to have a solid and a liquid. You could have two liquids. Calculations for power stations and how much water flow needs to go through the cooling systems to keep it cool enough. Same with motor design. All of that is all about this idea here. Okay, and it's just checking, as it says there, the heat lost from one of them is equal to the heat gained by the other, and that's how your equation works. Energy in, energy out. Okay, but big caveat at the bottom, not in A-level questions, but do remember that in real life you're also going to get heat transfer to the surroundings. Okay, and definitely this will be in a question. If you've got a liquid, you have to include the container as well. Okay, often something like a copper calorimeter, so it's a known mass, and you can work that out as well. Again, look at the PowerPoint, and that takes you through some examples, and then get plenty of. So thanks very much for that. Hopefully that's been nice and straightforward. This is now the ideal chance to put a revision visualization together. Before we go into these gas laws and how specific examples behave, and the derivation that's quite hard, or quite big rather, before we go into that, get a really good picture on this. So I would suggest a big diagram stroke mind map idea of particles, that vibration, their internal energy, that potential energy in some cases, not in gases but in the others, yes, and how those go visually with the latent heat, specific heat capacity, and the ideas around that. So a really good picture will really get that driven into your head, so you've got a really nice visualization.